workshop for science teachers every June, which has both Illinois continuing education credit and can also earn you graduate credit hours. And STEM in your science classroom, the new program where we will bring this scanning electron microscope into your classroom with one of our teachers. We do have a retired science teacher on our staff, and spend the day working with you with a microscope. So we just want to briefly the difference between light microscopes and SEMs. First, photons of light versus an electron gun, which we'll go over a little bit. Real-time imaging through your microscope or the cameras that are used today versus non-real-time. Magnification ranges are dramatically different, although about 100,000 is the average for an SEM. Color versus grayscale, so you don't see anything in color through an SEM. The sample prep's a lot simpler with light microscopy. Yeah, you have to do a wet mount or a permanent mount or maybe some fluorescent fluorochrome upgrade, but you have to do a lot more elaborate with a SEM. You need to have conductivity. So you sometimes have to coat the specimens with either carbon or gold or platinum. And it takes a little bit more effort. And of course the cost is dramatically different. This is in your program. You've seen it, just a quick idea of where we are from the human eye down to the highest TEMs that we have in use today. We're actually now looking at picometers when we resolve and measure it. A quick schematic also in your book. Instead of the light bulb, we're using an electron gun. The condenser lens, all electronic versus optical. We only bombard the top of the specimen. It's a reflected light only concept. This is what the electron gun is. It's actually a filament, it's like a light bulb. And we heat that filament. It's in what's known as a Waynaud cylinder. Think of it as a funnel to control the electrons in the escape. We have an anode, which is volted with very high voltage, so 1,000 to 30,000 volts. And then the electrons come out the gun. And it looks like this. So we're using just a 6 volt to activate the electrons on that coil. We're applying up to 30,000 volts onto this anode, and it creates the electrons coming out at a speed of 1 times 10 to the 7th meters per second. So it's moving very fast. Those electrons hit the specimen, and they actually bombard all of the electrons on the surface. We're talking a few microns. And those electrons then escape from the sample. So we have different aspects. Here's copper, and we use different voltages, and you get different size and penetration in the specimen. Also, your atomic number, aluminum versus gold. We have 2 different types of SEM images. We have your secondary image, which is used for your surface imaging, just qualitative imaging, and you have a backscatter image, which allows you to see some of the elemental aspects of the specimen you're looking at. So here you've got what looks like an aluminum oxide ball, but actually it's aluminum with stainless steel inclusions. This is what's known as the interaction volume. This is where the electrons actually hit the specimen. And again, only talking a few microns. But we get our secondary electrons give us a secondary image. The backscatter electrons come in here, roughly about 100 nanometers to a micron below the surface. These characteristic X-rays and these continued fluorescence and Auger electrons are all what are used to create the elemental map of what that subject specimen is. So what we're going to do is actually run through and do an EDS on a sample that we put into the scope. Jeff, I'll let you take it.
It's actually one of Jim's samples. Yes. Jim found a ring in his bedroom. Wasn't sure if it was gold or not. So we put it in the SEM. This is the SEM here, right? And it loads into this chamber here. This chamber door pops open. You put your sample in. You close it, and it pumps down, and it takes about 3 minutes. Right?
Pumps out to a vacuum.
The SEM itself has a magnification range of 10x to 60,000 times. So we love to bring this into schools and have teachers and students look at things with a magnifying glass and then with an optical microscope, and then put it in the SEM just to view the different ways that we can look at things. We talk about magnification and things like that. But here's our image here, and I'll click on this little filament key up at the top, and that might give us our live image. This is the edge of Jim's ring here. The way the software works, it's very user-friendly. It works kind of like a digital camera. So I can take my mouse and I can zoom in on my sample. There's a lot of auto features, auto brightness. And I can change all those manually as well. But what I want to do is I want to hit the sample with an X-ray. I want to get some sort of a spectrum off it and determine if Jim's ring is gold. So I'm going to go up here and I'll find an area. Increase my brightness a little. I'll zoom in with my mouse. And as I zoom in, my scale bar at the bottom changes. So I always have an idea on size and magnification. My magnification changes down here. I'll keep zooming in. I see there's some scratches on the surface of Jim's ring. A little chasm right there. But for now, I want to go ahead. I want to hit this with an X-ray. Let me go ahead and get my analysis. Now, y'all have to bear with me because this monitor is a little quirky. So, I'm going to start the process of gathering a spectrum.
I'm going to take an image, and that image is what will be used to actually analyze compound specimen. And this is a step-by-step little map to take you through it. Little wizard. Makes it very simple and intuitive.
Capture my SEM image. Now I have to determine which part of that image I want to analyze. I can take a spot. I can take a full area. I can do an X-ray map. I'll just do a spot analysis. And I'll move my spot around. I'll just choose any area. Go right there in the middle.
Now, we're building our spectrum. We have a 60-second time frame